Hello, I'm Ed Murphy with the Astronomy Department at the University of Virginia, and this is Astronomy 1210, Introduction to the Sky and Solar System, Lecture 22, Tides. Now that we've seen Newton's description of gravity, let's put it to use. We're going to study tides for a moment because tides show us something interesting about gravity and how the force of gravity changes with distance. So we'll get into the details here in a minute, but first of all, let's start with this image. I like this image, first of all, just because it's kind of a sad image. It's a fairly sad-looking horse with a boat that looks beached there. But what we realize by looking at the two cranes, the booms that are out over the side of the boat, is in fact this boat was intentionally beached like this. And long ago, this is how boats were unloaded. You would bring the boat in close to shore at high tide. You would wait for the tide to go out, and then you could bring a carriage out next to the boat, use these booms to lower the cargo down onto the carriage, and then take the cargo off the boat. So this would be a common way of loading and unloading boats long ago, taking advantages of the tides where you don't have a port where you can pull the ship up next to a pier. So real quick about tides, I just want you to answer this question. True or false? Most coastal locations on Earth experience one high tide and one low tide every day. So go ahead and go out to Learning Catalytics right now. Take a few seconds to answer this question. True or false? Most coastal locations on Earth experience one high tide and one low tide every day. All right, welcome back. So what's the answer to this one? We'll see the answer here in a second, but let me show you a couple of videos. So the first one is an animated GIF here, but the graphic is kind of crude, which is the Bay of Fundy. The Bay of Fundy in eastern Canada, up in New Brunswick, has the highest tides on Earth, or the greatest, I should say, the greatest tidal range on Earth between low tide and high tide. You can see at low tide there, that boat is actually on the ground and beached, and at high tide, the boat is all the way up here at the top of the pier. Here is another video. This one's somewhat higher resolution. Now, watch as the water comes in, watch the boats rise up. As you can imagine, if this is the top of the pier up here, they're probably going to rise all the way up to the top of the pier and come back down. Watch as it happens during the course of the day. And you can tell the passage of time by watching the shadows over here. If you look over on the left side of the video, you can see some shadows, and you will watch them move as the day goes on. So here is a movie of the tides in the Bay of Fundy up in Nova Scotia and New Brunswick, Canada. See the tide going out, and now the boats are back on the bottom. So, what is it about the Bay of Fundy? Why are the tides so high there? And this is the most important thing that I'm going to tell you about the tides, and that is the range of the tides, more than anything else, depend on the geography of your local location. So let's look at what happens in the Bay of Fundy. So here is New Brunswick, Nova Scotia up in Canada. This is the Gulf of Maine. So for example, here is Massachusetts down here. So we've got New England up here, and we've got New Brunswick and Nova Scotia right there. So we've got the large Gulf of Maine. And imagine during a high tide, all the water flows into the Gulf of Maine. And then it gets funneled up into the Bay of Fundy. And as it gets funneled up into the Bay of Fundy, the bay gets shallower and shallower as you get higher and higher. And it also gets narrower and narrower. So all that water that came into the Gulf of Maine, as it gets funneled up the Bay of Fundy, it has no place to go but up, because the bay is getting shallower and it's getting narrower, and that pushes the water upward. Up here at the very top of the Bay of Fundy, the tidal range can be 16 meters, which is almost 50 feet from low tide to high tide, and those are the highest tides anywhere on Earth. But here's the important thing to remember. It's all about the geography. The reason the Bay of Fundy has much higher tides than any place else on Earth is because of the unique geography of the area. Another place like this is Mont Saint-Michel in Normandy, France. It's an ancient medieval town, a city that was built on a rock that at various times is surrounded by water or is connected to land by a land bridge. So there's Mont Saint-Michel during low tide. So during low tide, you can see this sandy area out there around it. And here it is with the tide moving, and then here it is at high tide. Now today they have built a causeway, and the causeway is always above water. So the residents of Mont Saint-Michel can park their cars there and tourists can get in and out. But you can imagine why you would build a city on an island like this. It's impossible to siege a city like this because in order to do so, you would have to send your army out here, out onto the flats out here. They would have to build, say, siege towers to breach the walls here. But you will have the high tide rolling in, and suddenly you and your army will find themselves underwater. So this made it a very defensible location. Mont Saint-Michel, here are pictures that are taken of the causeway at low tide and the causeway at high tide. So you can see the roadway going off in the distance, and here at low tide, not only are there cars parked on the causeway itself, but there are buses and cars parked down on the beach. And then by the time high tide comes in, all of that is underwater. You can find some interesting videos on the internet of cars that are left behind and what happens as the tide rolls in. In the end, most locations on Earth get 2 high tides and 2 low tides every day. That is, you get a high tide and 6 hours later a low tide, and 6 hours after that a high tide, and 6 hours after that a low tide. So if you ever visit Mont Saint-Michel, keep in mind that you get 2 high tides every day. And so if you park out there at low tide, you only have a few hours to see Mont Saint-Michel before the tide comes in. You certainly don't have 12 hours. So just keep that in mind if you ever visit. So why is it that we get 2 high tides and 2 low tides every day? What we're going to do is we're going to build up a model of the tides, but we're going to do a very simple model. And our simple model is going to ignore geography. Because the geography of every location on Earth constantly changes, the tides are very specific to a specific location, like Mont Saint-Michel or the Bay of Fundy. The other thing I'm going to tell you about the tides is the timing of the tides is different than an ideal situation. We will learn how you can time the tides a little bit later on, or what kind of tide you should be experiencing. But here's the thing to keep in mind. That changes depending on where you are. So for example, in the Gulf of Maine here, when all that water rushes in, it takes time for that high tide to work its way up to the top of the bay. It takes time for that water to drain back out. The high tide up here at the top of the bay occurs much later than it does at the entrance to the bay. And that high tide persists longer than it does down here because it takes time for that water to drain out. So just know that at your location, typically the tidal strength and the timing of the tides will not match the very simple model that we create in this class, and that is almost all due to geography. Okay? But nevertheless, let's talk about what causes the tides. The tides are caused by Newton's law of gravity, and in particular the formula for Newton's law of gravity, which you'll remember from the last lecture is that the force of gravity is G times the mass of the first body times the mass of the second body divided by the distance between the centers of the bodies squared. And it's that distance that causes tides. And that distance causes tides because the further away something is, the weaker the force of gravity. So let me give you an example of this. Let's imagine that we have a planet, and for some reason I've stacked 3 billiard balls next to the planet. And these 3 billiard balls are touching one another. But here's the thing. Billiard ball number 3 is slightly closer to the planet than billiard ball number 1. So the force on billiard ball number 3 is going to be greater than the force on billiard ball number 1. So if we let them go a little while later, they've all moved. And they've moved because they've been accelerated towards the planet by gravity. But because the force acting on 3 was greater than the force acting on 1, because 3 is closer to the planet than 1 is, 3 will have been accelerated a bit more. It will have moved a bit farther. 2 will have moved an intermediate distance, and 1 will have moved the least of all, because the force acting on it was the smallest of the 3 forces. Now imagine what you see if you're standing on billiard ball 2. Imagine that you're a little tiny person standing on billiard ball 2. What do you see? Well, what you see is that billiard ball 3 is pulled away from you, and billiard ball 1 is pulled away from you. So what you see from 2 is a stretching. You see 1 and 3 getting pulled away from you. Now, what are the consequences of this on the Earth? The consequences of this on the Earth. So here's the North Pole of the Earth. So we're looking down on the North Pole of the Earth. And here's the moon, and it's not to scale. Remember, if we were to draw this to scale, the moon would have to be a lot further than this away from the Earth, but we want to keep the graphic reasonable, so we're not going to put the moon that far away. So there's the moon. Because of the distance effect, the moon is pulling more strongly on the water on the near side of the Earth than it is on the far side of the Earth. And it is pulling more strongly on the center of the Earth than it is on the water on the far side of the Earth, but it's pulling less strongly on the center of the Earth than the water close to us. That is, the force of gravity from the moon is the greatest here, it is the weakest there, and it is in between here at the center of the Earth. And over here at the edges of the Earth, there is also a component of the moon's gravity. You'll notice that the water is not getting pulled just towards the moon, but it's actually getting pulled a little bit towards the center. That is, if we broke this into 2 components, there's one component towards the center of the Earth and one that is straight out that way. So this water on the edges is feeling a little bit of compression. Now, the thing is, the Earth is a solid, and so for the most part, the whole Earth behaves as one ball. So what we can do is we can subtract off the force of gravity that's pulling on the solid Earth and see what's left over. And when we subtract the force of gravity from the moon on the solid Earth, because the whole Earth is moving together, and we look at the residuals of what's left over, because the force of gravity here was greater than the force on the center, there's a little residual force that points towards the moon. Here, because the force on the center was greater than the force on the moon there's a residual and it points in that direction. Here at the sides, because there was this little downward slant to those arrows, there's an inward pull. The consequence of all this is that if we look at the distribution of forces across the surface of the Earth, here and here, the water is getting pulled away from the surface of the Earth, and here it is getting pushed towards the surface of the Earth. That is, if the water is free to flow across the surface of the Earth with the moon, we get a high tide directly below the moon, and we get another high tide on the opposite side of the Earth, opposite the moon. And we get low tides at right angles to those. Now let me repeat that again. So the moon raises a high tide here, and it raises a high tide here, and it raises a low tide there and a low tide there. Now, I think most people have an easy time understanding where this high tide comes from, right? The moon, and again, this is not to scale, the moon is pulling more strongly on this water than it is on the Earth. And so it's pulling this water away from the Earth. So it's kind of easy to see why that high tide is here. It's really hard to see why that high tide is there. And the answer to why we have a high tide here is, remember, the moon is pulling more strongly on the Earth than it's pulling on that water. It is literally pulling the Earth out from under that water. This water is getting left behind. So we have 2 high tides, a high tide here and a high tide here, and a low tide here and a low tide here. Now remember, the Earth is rotating from west to east, so as seen from the North Pole like this, it's rotating counterclockwise. So as the Earth rotates from west to east, you get carried under the high tide, and about 6 hours later you get a low tide, and about 6 hours after that you get a high tide, and 6 hours after that you get a low tide. So in a day, in the length of time it takes you to go all the way around the Earth and come around once, you get a high tide, low tide, high tide, low tide. You get 2 high tides and 2 low tides. The high tides are about 12 hours apart, and the low tides are about 12 hours apart. Now, it turns out they're going to be a little bit less than 12 hours apart. I'm sorry, a little bit more than 12 hours apart. And the reason for that is the moon's not sitting still. And as the moon moves over here, if we experience a high tide now, as the moon orbits around the Earth, it's going to take a little bit more than one rotation of the Earth before we get this high tide over here 24 hours later. In fact, the moon moves about 50 minutes or so a day. And so the high tides that we experience today, we will get this high tide. Tomorrow, that same high tide will occur on average about 50 minutes later, and the day after about 50 minutes after that, and the day after about 50 minutes after that. And that's because the moon is orbiting around the Earth. Now, here's the interesting thing. We can combine the tides that we're getting from the moon with our knowledge of the phases of the moon and where the moon is at different times to be able to answer a really cool question like this. It's around sunset, and there's a first quarter moon in the sky. What kind of tide am I experiencing? Am I experiencing a low tide, a high tide, or neither? Is it in between high tide and low tide? So I want you to go out to Learning Catalytics and I want you to answer this question. It's around sunset with a first quarter moon in the sky. What kind of tide am I experiencing? Okay, welcome back. Were you able to figure this one out? So let's go back to our trusty diagram of the phases of the moon right here. And let's talk about the tides. All right, so in our problem, we said it was sunset and there's a first quarter moon in the sky. So it is sunset, so this is where I'm located on the Earth. And there's a first quarter moon in the sky, so this is where the moon is located. And the question then is, what kind of tides am I experiencing? Well, if I'm standing here and the moon is there, the moon raises a high tide here and a high tide here, a low tide here and a low tide here, which means at that moment in time, at sunset, with a first quarter moon in the sky, I am should be experiencing a high tide. If it were sunrise, I'd be experiencing high tide. But if it was midnight or noon, I would be experiencing a low tide. Now, here's the thing about this problem. I'm sure at some point in your life, you're going to run out to the beach and you're going to say it's sunset and you're going to look up and see a first quarter moon in the sky. And you're going to say, Professor Murphy told me I should be experiencing a high tide. And you'll find out that you're experiencing something else. And remember, that's almost certainly due to geography and the change in the land and the fact that the tides are a lot more complicated than the simple model that we're demonstrating here. But that is the causes of our tides. All right, so let's talk more about the tides. The moon raises tides on the Earth. Now, the reason the tides on the Earth are so noticeable is because water is free to slosh and move around. And the height of the tides depends on local conditions. It can be as little as 30 centimeters, so 30 centimeters is about a foot or so, and it can be as much as we saw up at the top of the Bay of Fundy up there, as much as 16 meters. Okay, and there are 2 high tides and 2 low tides every day. It turns out that the moon can also distort the solid shape of the Earth. We call these solid body tides, and it turns out the moon is actually squeezing the Earth enough that it's actually distorting the shape of the Earth. And the moon is distorting the Earth so that the land is actually moving up and down, and the solid Earth can rise and fall by as much as 20 centimeters or more. So not only is the water sloshing around, but the moon is actually deforming the Earth, and the solid Earth rises and lowers. We don't notice the solid Earth going up and down by as much as 20 centimeters because everything around you is going up with you and everything around you is going down during the course of a day. Now, it turns out the moon is not the only thing that raises tides on the Earth. The sun raises tides as well. And although the sun is much, 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 much more massive than the moon, it is also a lot farther away. And because the force of gravity drops off as the distance squared, remember the equation is g m1 m2 over the distance squared. Because the sun is so much farther away, its gravity is weaker when it comes to causing the tides. And so it turns out that although the sun is a lot more massive than the moon, its tides are about half the tidal force of the moon. That is, the sun raises tides on Earth as well. It's just that those tides are only half the force of the tides that we get from the moon. Now, the tidal force from the sun can either add to or subtract from the lunar tides. And so that raises the fact that sometimes we get particularly high tides. And that's when the high tides from the sun are adding to the high tides from the moon, and they're constructively adding together. But sometimes the tides just aren't very big, and that's what usually happens when the high tide from the sun is canceling out the low tide from the moon. And the high tide from the moon is canceling out the low tide, is being canceled by the low tide from the sun. And what we call these are spring and neap tides. Spring tides occur during new and full moons, and it's during this time that the tides are higher than average. Now, the first thing, before we talk about the details of this, I just need to say spring has nothing at all to do with the seasons. Make a note for yourself right here in your notes. Spring has nothing to do with the seasons. It has to do with the fact that the tides seem to spring up very suddenly, but it has nothing to do with the seasons. We'll come back to neap tides in a minute. So here's a spring tide. A spring tide occurs at a new moon or a full moon. Because during new moon, let's do new moon for a second. During a new moon, we get a high tide here and a high tide here. But it turns out the sun is also creating a high tide here and a high tide here. And the sun is creating a low tide there and a low tide there. And the moon is creating a low tide there and a low tide there. So because the high tide from the sun and the high tide from the moon are adding together, we get a particularly high tide. And we get that high tide here, and we get that high tide here. We get a low tide here and a low tide here. So these are the spring tides, when the high tides from the moon and the high tides from the sun are adding together. Let's talk about neap tides. So let's talk about the sun first of all. The sun is going to raise a high tide here, right? It's pulling more strongly on this water. So the sun is going to raise a high tide here. And the sun is also going to raise a high tide over here because it's pulling more strongly on the earth than it is on that water, and it's accelerating the earth out from underneath that water there. So there's going to be a high tide left behind over here. But the sun's high tides are only half the high tides of the moon. So the moon here is raising a high tide. So imagine a first quarter moon, because neap tides, I should have said this, neap tides occur at the time of the first quarter moon and the third or last quarter moon. And that's because the moon is raising a high tide here and a high tide here, but the moon is creating a low tide here and a low tide here. Well, the high tide from the sun is canceling the low tide from the moon, and the low tide from the sun is canceling the high tide from the moon. Now, ultimately, the moon's going to win here because it creates the bigger tides, but the tides are going to be smaller than average. And so at first quarter moon and at last quarter moon, we get neap tides, where the tides are not as high as average. Whereas here, we get much higher than average at spring tides. When the moon is new or the moon is full, we get much higher than average tides. So that's the definition of spring tides and neap tides. So let me ask this question. Go ahead out to Learning Catalytics and answer this question. How often do spring tides occur? Do spring tides occur once a month, twice a month, 4 times a month, only around March 21st, or around March 21st and September 21st? So go to Learning Catalytics and answer this question. How many times do spring tides occur every month? All right, what did you get for this one? Well, remember that spring tides occur at new moon and again at full moon. And so if spring tides occur at new moon, we get 1 new moon a month, but they also occur at full moon. So we get 2 sets of spring tides every month. So the spring tides occur twice a month. Neap tides occur twice a month. All right, so let's talk about some of the interesting effects of, and I should come back to this page. If you're interested, a graduate of UVA by the name of Phil Plait. Phil and I were graduate students here at the University of Virginia together. He and I were good friends in our time here at UVA. He went on to create a website called badastronomy.com. He studies a lot of misconceptions in astronomy, and he's got a great set of pages about the tides. If you're interested in learning more about the tides, you can just Google bad astronomy and tides, and you can find his pages on the tides. All right, a couple of other interesting things. Not only does the moon raise tides on the earth, but the earth raises tides on the moon. We saw a second ago that the moon actually distorts the shape of the earth. It actually bends the earth so that the solid land rises and falls. Well, the earth does the same thing to the moon. But here's the problem. The Earth is 81 times the mass of the moon. So for the tides that the moon raises on the Earth raises even larger tides on the moon. And so the Earth has very significant effects on the moon. Now, one of these effects is called synchronous rotation. You'll remember when we talked about the lunar lunacy lecture, we talked about the fact that the moon rotates once for every revolution. That is, the moon's orbital period, the length of time it takes to orbit the Earth, and the moon's rotation period, the length of time it takes to spin on its axis, are equal to one another. And we call this synchronous rotation, the fact that the moon rotates once for every revolution around the Earth. Way back when the moon formed billions of years ago, it probably rotated much faster. But over time, the tidal forces from the Earth have slowed the moon down. And in fact, they've locked the moon so that the heavy face of the moon is facing towards the Earth. And we've ended up with this unique situation. I shouldn't say unique because it's common in the solar system, this interesting situation where the moon always keeps the same face towards the Earth. And we call that synchronous rotation. And as I said, it's not unique at all. It turns out that many of the moons of Jupiter, Jupiter's moons Io, Europa, and Ganymede all keep the same face towards Jupiter. Mercury has a synchronous rotation with the sun. Pluto and its moon Charon both synchronously rotate. That is, Pluto always Pluto's moon Charon always keeps the same face towards Pluto, and Pluto always keeps the same face towards Charon, and the two of them always face one another. All right, that is synchronous rotation. That is one of the consequences of the tides. Another consequence of the tides is that the moon is slowing down the rotation of the Earth. So a minute ago, I showed you this diagram where we've got the Earth spinning on its axis, and we've got the moon, and the moon raises a high tide here and a high tide here. But the problem is the Earth is spinning so fast, the Earth is spinning once every 24 hours, that by the time gravity gathers this water together and we raise the high tide, the rotation of the Earth actually pulls that bulge out in front of the moon. Now, here's the thing about that bulge. This figure here is grossly exaggerated. The moon's bulge is barely in front of the moon. It is not nearly this far, but to demonstrate what's going on, they've grossly exaggerated how far this bulge precedes the moon here. But it's important to know that this bulge doesn't sit directly below the moon. The rapid rotation of the Earth carries that bulge out in front of the moon. Because that bulge is in front of the moon, it has two effects. The first one is it is pulling the moon forward in its orbit, and that means it is speeding up the moon. And if you go back to the circular orbit velocity equation that you saw last time, if we speed up the moon, it turns out the moon is going to move to a higher orbit. So one consequence of this is that the moon is speeding up in its orbit, but it's also pulling away from us. Another consequence of this bulge being out in front of the moon is that the moon is pulling backwards on the bulge, and that is slowing the Earth's rotation down. So the forward pull on the moon makes the moon spiral into a higher orbit, but friction between the Earth and the oceans makes the Earth rotate more slowly. The moon is pulling backwards on that bulge, and that is slowing this bulge down. It is slowing down the rotation of the Earth. So the tidal effects are actually causing the moon to recede from the Earth at the rate of about 4 centimeters per year. That is, every year, the moon pulls about 4 centimeters. That's 4 centimeters right there. The moon pulls that much further away from us. We can actually measure this as part of the Apollo missions. On a number of the landings, astronauts installed prisms on the surface of the moon so that we can send a laser up to the moon, and it bounces off those prisms, and the laser comes right back. And because we have precisely determined the speed that light travels, we can measure how far out it goes and how quickly it goes out and how quickly it comes back. We can precisely measure the distance to the moon, and we can easily see the moon receding from us at a distance of about 4 centimeters per year. But the other consequence of this is that the day is slowing down. The length of our day is growing by about 0.0023 seconds per century. Now, that doesn't sound like a lot. That's 2/1000ths of a second per century. But that's the length of every single day. And so you can imagine in a year in which we have 365 days, or in 3 years where we have about 1,000 days, it soon adds up. And so the length of a day growing by 0.0023 seconds per century over time has significant consequences. One of those consequences is that fossil evidence of marine animals and tidal sediments long ago indicated that about 900 million years ago, the length of the day was only 18 hours. That is, 900 million years ago, the Earth spun once every 18 hours, as opposed to the once every 24 hours we get today. Another consequence of this is that some time ago, scientists stopped using the rotation of the Earth as our standard for time and started using atomic clocks. And the reason we did this is we knew that the Earth was slowing down because of these effects. And the problem with using the rotation of the Earth, 60 seconds in a minute, 60 minutes in an hour, 24 hours in a day, is that the length of the days are getting longer. And that makes it hard to do precision work if the length of the day is always changing. So in the 20th century, scientists stopped using the length of a day, and they defined the length of a second to be a certain number of cycles of a particular atom in an atomic clock. And because atoms are the same everywhere in the universe, and they're the same everywhere on Earth, and they don't change with time, this time, as defined by an atomic clock, means that time is no longer speeding up or slowing down as the Earth speeds up or slows down. Every now and then, though, our atomic clocks get out of synchrony with the rotation of the Earth, and scientists have to add an extra second to our calculator, or to our calendar. And once every couple years, you will hear that scientists are adding a leap second to the calendar. And what that means is that at midnight on December 31st, at 11:59 p.m., the clock will strike 12:00:00. And then we add another second into the clock so that it will strike 12:00:00 again before moving on. That is, we add an extra second at the end of the year. And that's to keep the Earth's calendar, the Earth's rotation, in sync with our atomic clocks. Interestingly, there's an interesting consequence of the fact that the moon is pulling away from us and the Earth is slowing down. Billions of years from now, the Earth's rotation will be tidally locked to the moon. Just like Pluto and its moon Charon, our Earth and our moon will be tidally locked to one another. The moon already keeps the same face towards the Earth, but the Earth will keep the same face towards the sun. And the Earth will have slowed down enough that it will take 47 days for the Earth to rotate once on its axis. And it'll take 47 days for the moon to revolve around the Earth. But at this point, because the Earth's rotation and the moon's revolution are the same, these tidal forces will no longer cause the moon to recede from the Earth. And so we won't lose the moon. Just because it's pulling away from us at 4 centimeters per year doesn't mean that we're necessarily going to move it. The rate at which it pulls away from us is going to slow down over time, and eventually it will come to a halt. And billions of years from now, the Earth and the moon will keep the same face towards one another. The moon will orbit the Earth every 47 days. The moon will turn on its axis every 47 days, and the Earth will turn on its axis once every 47 days. However, that's going to take so long that it is likely that the sun will die before that. So this concludes our study of Newton's laws, Newton's law of gravity, and one consequence of the law of gravity, which are tides. Now we're going to move into a completely different part of the class. We're going to start studying our solar system. So in our next lecture, we're going to take a tour of the solar system and learn about the different kinds of bodies we have in our solar system. So please join me in our next lecture, Introduction to the Solar System, when we begin the second half of the class. It's Introduction to the Sky and Solar System. We are now done with the sky, and it is time to study the solar system.